Welcome back to our series on Year 1 statistics. And in this series, we'll be going through all of the different chapters you need to know about to sit your A-level exams. So in this video, we'll be looking at correlation, and more particularly what is correlation and what is linear regression. And as well as looking at these topics, we'll also be looking at a few questions so you can, better familiarize yourself with some of the different questions that are out there. So we'll go over some theory and we'll look at some examples, and hopefully put together, it will really help you to understand this topic much better. So some of the key takeaways we want you to have from this chapter is understanding what is bivariate data, understanding what is correlation and why that doesn't mean you have causation, as well as what is the linear line equation and when to use this. So we'll be looking at all of these three different areas. So just going further down here, let's start off with what is bivariate data. So bivariate data is usually when you're looking at two different variables usually. So if I had to put it in a better way, I'd say bivariate statistics looks at how one variable compares with another variable. So how does it influence it? So some good examples of this would be, let's say you're looking at someone's height and someone's weight. So on one side of the graph, what we might have over here is, let's say we've got a graph like this. And looking on this graph, on this side, we might have someone's weight. And on the other side, we'll have someone's height. So we want to look at the correlation between these two things. So in bivariate data, if I have a single data point right here, for example, this point incorporates both what someone's weight is. So you might have this one person's weight is like 60 kilograms, and the height might be 165 centimeters. So this is bivariate data. And the reason this is bivariate data is, as you can see, we have two different sets of data. So bivariate data can be anything. I could have how far you've been able to run compared to how long you've been in the gym, what your weight is compared to how much you eat, and lots of different things like that. So usually when you're looking at this, you might have learnt this at GCSEs. The area we're looking at the bottom of the graph, so that's the x-axis, this part here is considered your independent variable. So that's your independent variable here. And that's the variable which, that's the one that you're trying to control. That's the one that you don't want to, that's the one that you're actually saying, okay, look, well, if I'm changing my height, what happens to my weight? So it's saying that if I change the independent variable, how does my other variable change? And this other variable that we talk about, which is everything on the y-axis here, this is going to be considered as your dependent variable. So put together, that's what you've got. And this is the variable which you measure. So if I had to summarize what we said, the independent variable, so independent variable, this is the one which you control. So this is your controlled variable. Controlled variable. And your dependent variable is your measured variable. So this is what you are trying to measure. So yeah, put together, that's kind of what you're looking at for bivariate data. So that's just hopefully going to give you a better idea of how bivariate data works and what that means. So normally when you look at these different sets of data, if I then move further down, so looking further on, there are a few different things you might want to know. So let's draw a few graphs here first. Let's look a little bit at what do we mean by correlation. So if I just copy over that graph, show you all the different types of graphs we can have. Okay, so now looking at this one, let's start off with what is positive correlation. So positive correlation. Positive correlation is where your data points as you're drawing them are somewhat going on an upwards trend, and in general they are going slightly up. So looking at this graph, you can see if you're low on the graph, you're quite likely to have a lower value for one than the other. So if this value is low, then this value is also low. And on the other side, if this value is high, then this value is also likely to be high. This is what we consider as weak positive correlation. However, if your points are going up, but there's a much clearer kind of pattern in it, so something like this, you can see the points are much closer together, and you can more accurately say where your points should lie. So again, you can see why it's positive correlation, because it's going upwards. This is considered as strong positive correlation. So that's how these two areas work. So now let's say that we were looking at our other side. So you can probably figure it out. if that's what is known as positive correlation, we also have something known as negative correlation. So if we copy this over again, over here, and just put that down here, what we'll be looking at now is some weak correlation. So to be honest, it's just pretty much the same thing. Negative correlation. And this is where your points are all going down slightly. So, you know, there's not a very obvious downwards trend, but there is somewhat of a downwards trend if you take a look at this. Whereas again, with the strong negative correlation, it's very clear that the points are going down. So if I had to, again, draw a line of best fit through each of these different things, if I was drawing it through here, it'd be something like that. Through here, it'd be something like that. And then here would be something like that. And here would be something like that. So just to reiterate, this is again weak negative correlation. Oops, this is known as weak negative correlation, and this is strong negative correlation. And you might be wondering, what does no correlation look like? So if you want to know what that's like, if I draw that down here, then no correlation is where you can't really see a pattern either way. So it's kind of like your points are randomly scattered across your graph and there's no obvious trend going up, going down, or going anywhere. So here there is no correlation because we can't really draw any such line of best fit through it. There's not really any correlation there. So that's what it means to have correlation. So in your exam you'd be expected to identify the different kinds of correlation that you may have between different variables. So what you say is, for negatively correlated variables, if you want just like a nice phrase, so for negatively correlated variables, what happens is as one variable increases, the other will decrease. So one variable goes up, the other variable goes down. That's what it means to be negatively correlated. And if you're positively correlated, variables, spelled that wrong there, then it means as one variable goes up, the other variable will go up as well. So just to show that on the graphs up here, you can see on the positive correlation side over here that as one variable here is going up, the other one is also going up, and here you can also see as they're going up, they're also going up. But here you can see as one is going down, then the other one is also going down. So that's just how you work with the different areas of correlation. So hopefully that makes a lot more sense now. So apart from this, the next area that we will need to look at is to do with, if I just go through it, is linear regression. Now this is a topic which might look like there's a lot I'm drawing at the beginning, but it's not a very difficult chapter to understand. So let's take a look at what is linear regression. So linear regression. Cool. So now for linear regression, what happens is normally let's say we have a diagram. So let's just draw a nice large scatter diagram. And in the scatter diagram, what we find is that we have a bunch of points through our graph. So actually, let's not have one there. Let's have one here, 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 and let's say there. So looking at this graph, you'd say, you know, there is some sort of line of best fit you can draw, and you'd say there is probably a weak positive correlation, or depending on how close they are, I could even say it's a strong one. But if I told you to draw a line of best fit, some of you might draw a line of best fit which is like that. Some of you might draw me a line which is like that. Some of you might draw me a line which is like that, or like that, or like that. And to be honest, all of them could seem as if they're all correct. But if you want to find out what is the exact line of best fit, we use a method known as least squares of regression. And this is basically the regression line that we're talking about. And what this line is doing is, let's say we draw a line of best fit which is, actually let's do this. Let's draw two lines of best fit. Let's draw one which is kind of going through like that. And then let's draw another one in a different color, which is going through somewhat, let's say, something like that. Okay. So if I have this as my line of best fit, what the idea is you have a bunch of distances from each of these points, which will meet this line. So let's go up. So each of these points have a distance where they meet this line. And what you want to do is, if I call this D1, D2, D3, D4, call this one D5 and D6, D7. The idea is that D1 added all the way on to D7 equals to some number. And if I do the same thing for, that would probably reach up there somewhere. This one reaches there, this one is up there, this one's down there, this one's up there. Just drawing on, should probably have continued the line, but you get the idea. Now again, these would be, let's call this one like B1, B2, B3, B4, B5, B6, and B7. Then if I added up all of these lines, eventually I get another number. Now, different lines I draw will have different distances from each of the points. Now, the thing is, you can probably tell by looking at this graph that if I add up all the orange lines, which are the B1, B2, and so on, that if I add them up, the final total I get will be much bigger than the total I'll get for the lines which are in blue. So what that would suggest is that the blue line is a better fit than the other line. And what you're trying to do in least squares regression is you're actually trying to find the data points which will actually minimize this maximum distance. So if you can draw a line where if I have like B1, B2, B3, and you can make that as small as possible, then that is considered the least square regression line. And that's what this kind of topic is about. So this is the idea kind of behind it. You want to minimize the sum of the squares of the distances of each of the points. So that's kind of what you're doing in that. That's a very high level simplified version, just to give you a conceptual understanding. We can look at it more deeply in another video, but that's kind of the idea behind it. What you actually do in this video is, in this topic, is normally because let's say I had a line like this just on the side, let's say I had some random line like that. The thing is, the distances that I'd have between the points, these might be considered as positive and these might be considered as negative. So what I mean by that is this might have a distance of 2. This you might count as -2 over here. This might be like 5 and this might be considered like -6. So in order to get rid of all these minus signs which will interfere with what you say is you do something like 2 squared plus -2 squared plus 5 squared plus -6 squared. And the squaring part kind of gets rid of the minus sign so you can get some number which works. So that's why you call it the least squares regression line. But the good thing is for your exam, you don't need to actually be able to calculate this. You just need to understand the concept, which is why I explained the part before. So if that makes sense, what we can continue to look at now further down here is what is the regression line formula on its own. So the regression line of y on x is written in the form y equals to a plus bx. Now this will look very familiar to the line of the equation of a straight line, and that's because this is exactly the same equation as the equation of a straight line. As you know from your GCSEs, the equation of a straight line is y equals mx plus c, where the m is a gradient, the c is a y-intercept, and in this topic it's literally the same equation. The c is just an a and the m is just a b. So if you're thinking of y equals a plus bx, just think of it as literally the equation of a straight line. So what the b is trying to tell you is it's kind of telling you information about the correlation, because as you know, in any graph, if you have a line and this line is a straight line going in the positive direction, this has a positive gradient. Oops. And you have a positive gradient when your b or your m is positive. So if you know that, then you know you have positive correlation. And then the same thing counts for if you have negative correlation. So if you have a negative gradient, what do we know about our b? Well, we know b must be negative. So as soon as you see b is negative in your equation, you know that you have negative correlation. And that's basically the main idea. This is the kind of stuff that you can use to find out what is true about your bivariate data. because in your bivariate data, what you'll find is that if you can find, you'll usually be given in your exam what the value of B is, and they'll say something, and you also know what A is, and they usually say something like, okay, if your graph is like this, for example, let's say this is your graph, they'll say something like, and this is your X value, and this is your Y value. They'll say, okay, for a given value of X, which is an independent variable, can you predict what is the Y value going to be? So he might say, look, here's my line of best fit. It looks something like this. And then they will give you a value for X, which is, let's say, 100. And then the idea you have is that, okay, if I've got 100 here, I can predict what my Y value is supposed to be. And you might find here that your Y value should be something like 250. So you can use this equation to have a value of X and use that to predict the value of Y. So you're using your independent variable in order to predict your dependent variable. Now, what you cannot do in this one is use your dependent variables to figure out independent variables. So what I can't do, and what I'll do is I'll put this in red, is I can't say, oh, if this is 150, then I can work backwards and I can find out that this is actually meant to be 50. So this is actually wrong, and so you can't do it going that way, but you can do that. So you can use X to find Y using that equation, that's fine, but you can't use Y to find X, that's going to be wrong. So that's the idea of correlation in that chapter over there. So apart from that, what else you need to know is that if you know the value, so if I just say it formally, what I've said in like maths talk, you'd say if you know the value of the independent variable from your bivariate data, then you can use your regression line to make a prediction on the estimate, or the estimate which corresponds back to your dependent variable. So your regression line is used to make predictions for values of the dependent variable, basically. And usually you want it to be in the range of the data that you've been given. And what I mean by that is, let's say I had another situation where, let's say this is my graph. And in my graph, I've got a bunch of data points like this. So once again, got some of that. So based on that, you can definitely say that there's some sort of regression line, let's say like that you've come up with. Now, the problem is, it would be fairly okay for you to say, okay, I'm trying to make a prediction for something. Let's say I'm trying to predict what the value at this point here in X is. Let's just make up a number and say that's 90. Well, that's fine. I can just go up, go to the left, and I can say, okay, I've kind of predicted that this maybe is 160. That's the value I read of my y-axis. But then the problem is, let's say I had another very small variable here, which is like 5. If I keep going up, there is no line to hit. And the reason is that I don't have any data points on this side. If I had some extra data points, so let's say I had some more data points here and here, then I'd be able to extend this regression line, which I've got further, and that would be more accurate. But unfortunately, these points don't exist. So by trying to predict something outside of the given data, that might not be the most accurate thing to do. And sometimes the questions in the exam will have that as like the last question, like why is this value accurate? So why is 90 a good idea to use, but why is 5 not a good idea to use? And usually that's the answer. And another thing that you might want to know about this question is, another thing you could say to answer these questions is that, well, you can see that this would be more accurate if I had more data points. If I had a ton of data points like this, then I can say this blue line is fairly accurate. And sometimes you might not have that, and that's your value of n. So at the beginning of this drawing, back when I was doing this, I only had about, let's say, 6 or 8 variables, so n was 6, so that's not so accurate. Whereas now if I have, let's say, 20, that's slightly more accurate, and now let's say I had n as like 2000, then n would be much more accurate. So sometimes you can say the answer to these questions are that, the value of n is quite small, and hence your data might not be as accurate. So that's the idea behind regression in this chapter. Next, what we'll take a look at is how you can use these and how these are used in some of the questions that you'll do, and hopefully that will give you a much better understanding of this topic. So when it comes to some questions, let's take a look at an example. So let's say you're given a table as so, and it gives you a bunch of people and it tells you the age and it tells you their favorite number. So normally the questions you see will often give you a table and you have to draw some sort of scatter diagram from it. So as you can see here, it says, please draw a scatter diagram. So for that, let's try and draw out our diagram. So what it would look like is we draw our axes as so. And once we've done that, let's put down the age on the x-axis. And normally what you should write down is age in years, as it's given to you in your question normally, but this is just an example. And let's put down your favorite number. So if you were to just, draw this the usual way and plot it, you would find that your diagram would exhibit some sort of correlation, and your diagram would end up looking something like this. So that's just roughly what you would get if you should plot these points. And normally you'd get some marks for just drawing your scatter diagram properly, so make sure you do that right. And then the next thing you'll be asked to do is to describe the correlation between the 2 points that you have. So as you've seen before, when we've done this kind of thing, you can see there's a clear downwards trend, and you probably have a line of best fit, something like that. You don't have to draw it in, but this is just to demonstrate the point. You can see that you'd say there's probably a weak negative correlation between these points here that you've got. And then the next part of this question will ask you to interpret it. So this is normally the part where you have to put into words what you found. And what's important to understand here is you'd say that, well, I can see here that as the age increases, so as your age is going up, we find that the number, which is the favorite number of this person, also tends to actually decrease. So that's what you find with this kind of question. So normally what you do is you'll say something like, the thing that I found or saw on the x-axis, as this thing either increases or decreases, we find that the thing on the y-axis is also either increasing or decreasing. So depending obviously on whether it's positive or negative correlation, you'll change your answer. So in this case, because it's negative correlation, we'll say as the age is increasing, we find that the number, which is the favorite, is decreasing. But if we had positive correlation for a different question, we'd say as the x-axis thing is increasing, we find that the thing on the y-axis is also increasing. And what is important to mention at this point is that sometimes you might see things are correlated, but that doesn't imply that those two things cause each other. So you can only say two things cause each other if you change one thing. It means you definitely should be changing the other thing, like it causes a change in the other thing. But sometimes you might just find correlation between two different variables, but it doesn't necessarily mean a change in one variable is actually causing the change in the other variable. So that's just one thing to be careful with. So that's pretty simple with these kinds of questions. You draw your scatter diagram. Correlation is fairly simple. You can figure out if it's negative or positive, and you have to figure out if it's weak or strong. And apart from that, for the interpreting part, you now have a plan for how to do it. So you'll say, based on what I have in my x-axis over here, as this increases or decreases, the thing on my y-axis here is either increasing or decreasing. That's normally how you'll answer that kind of question. And yeah, just substitute it in. So here you've got age and number. You just choose whichever ones you've got. So that's how you do that kind of example. Now let's look at a different type of question that you might get. Another kind of question you might get is something like this. So you've got the same data as before, but now they've given you the equation of the regression line. So if I just go back, that might be the equation of this orange regression line that I've drawn in here. So the question is, what does that gradient mean about correlation? Well, the gradient over here is this part here, the minus 2.2x. And as we said before, a negative gradient means that you will have negative correlation. So the answer to this question is simply that we just have a negative correlation in our graph. So that's fairly simple to understand. Now, the next question that we have to answer is, can we actually use a regression line? And in order to understand this part here, what we need to see is that, when can we actually use this regression line? When is it always correct? And there's always like a set answer for this part. And that is the correlation of the data suggests there's a linear relationship between x and y, and therefore we can use a regression line. So the key parts of this question that we just saw is the part about having a linear relationship, and the correlation of this data is why we have this linear relationship, and therefore we can use a regression line. So when you see data and when it looks like it has some correlation where it's linear, so as one thing goes up a certain amount, the other thing also goes up a certain amount, what I mean by that is like your data looks something like this. So, it's something like that, it's something like this. Your data could be going somewhere like, somewhere like that, somewhere like this. Doesn't matter. All these are linear because as one goes down, the other one goes up or down in a certain amount. And if you wanted something which is non-linear, it looks something like that. That's non-linear. Something like this is non-linear. Something like this is non-linear, because it's not always the case as one goes down, the other goes up. or the other way around, because you can see it always changes depending on what part of the curve you're at. So the set answer you give for something like this is a correlation of the data suggests a linear relationship, and if you have a linear relationship, only then can you use regression line. So that's kind of the set answer you give for questions like this. So another example of kinds of questions you get would be something like this. So here we have a bunch of plants, and we've given the time in, let's say, in hours or days. Let's say days, the days for which these plants have been growing, and the height in centimeters for how much height they have achieved. The question gives you the regression line is y equals 8.85 plus 0.62x, and that's the question you've got so far. And it says that here, some estimate of a plant has been taken for 38 days. So they've found a plant, and they want to estimate what that plant would look like at 38 days. And the estimate of a plant is also found at 28 days. And then the question is saying, well, how accurate are these estimates? Well, in order to answer this kind of question, what we need to do first is we need to draw the graph. So again, this is just an example for now. It's not one of those worked ones, just want to understand the theory. So I'll just draw a normal graph. And here, if we were to plot all of these points onto a graph, what we would probably find is it's something like this in terms of the points which are plotted. This is roughly what they would look like. And if we just put in our line of best fit, you would have something like that. Now, the thing is, if you look back at this data, you'll notice that the biggest value that you have for the plant in terms of time, so just putting time on this axis here, and putting down the height on this axis here, what we are finding is that the biggest value I've got for time is 39. So you know that this value here for time is 39. And the smallest value we have is 32. So we have somewhere here 32. And also, my bad, I just realized that 42 is the largest time we've got there. So let's swap that out. So yeah, we've got 42 here. Now, for the first one which we're estimating, we estimated some plant at 38 days. And 38 days actually falls within our expected estimate of the line. So 38 falls here. And therefore we can be, fairly confident, somewhat confident that 38 would fall there. However, we've got another plant which is found to be at 28 days. And 28 days is probably somewhere all the way down here. Now, the problem, like we said before, is there's no line or no points that we have which extend the line there, because the smallest value we had before was 32. And because 28 falls outside that value, we can't really say that this estimate is as accurate, because we don't have no data points covering this side of the graph. Whereas for 38, we have plenty of data points covering this side of the graph. So that's why we would say that 38 is fairly accurate and can be considered more accurate than the value of 28, because 28 as a value falls outside of the interpolation that we have of our data, and it falls over here. So that's not correct. So that's why 28 doesn't work. The next question says that someone wants to find the time of a plant given the height of 36. So what that kind of implies is that, let's just go back a second. If I wanted to find out the height of a plant given the time, what I would do is I would input the time into the x value here, and then after I solve this equation, I will get what the height of the plant is. Now, the problem we have is in this question is saying that someone wants to find the height of a plant given the height. He wants to find the time of the plant. So they want to find what x is given this value of y. Now, the reason this is wrong is, like we said before, you can only use the independent variable in order to find the dependent variable. So now in this one, we have, this is our section, which is the independent side, and this is the dependent side. So we can't use a value over here on the y side to find a value here on the x side. So the reason that this is wrong, and if you had to give a reason for it, is to say the independent variable in this model is supposed to be time. However, we're trying to find the value for the height, which is the dependent variable, and you cannot be using an independent variable in order you can be using a dependent variable in order to find out an independent variable. So just to summarize, what we're trying to say is you cannot use this dependent variable in order to find this independent variable back here. You can only ever put a value of x to find a value of y. And that's usually the answer to these kinds of questions. What we'll do next time is, this kind of topic had more theory involved, so in terms of the answers, there weren't very many calculations. A lot of it was to do with explaining. In future videos, what we'll be doing is a lot of it is more calculation based, so we'll actually go through the full worked calculations from the beginning right to the end, and that way you'll have like fully worked solutions. And in this example, I just wanted you to really understand how the theory of these work. So these questions are quite similar to what you might get in the exams, and we'll do another video separately just purely going through exercises from the beginning to the end, where I fully write out what the worked solution should be and have some custom questions for you to try out, which will be related to this video, and that will come out soon, so look out for that. In the meantime, I hope you've understood correlation a bit better for exam board, and if you have any concepts that you did not understand or some theory you did not understand, just ask in the comments below and I will get back to you and let you know.